Welcome to section 1.3, day 3, limits and end behavior. Today's objective is to use limits to describe end behavior of functions. So end behavior describes how the function behaves at either end of a function. That is, what happens as the function increases or decreases without bound. So our x's become like negative infinity and infinity. So functions can approach positive infinity, negative infinity, or a value. There are some functions that will oscillate, like sine and cosine functions. They go back and forth between 1 and negative 1. But most of our functions are going to do one of the three things: infinity, negative infinity, or some value. So to check end behavior, we use limits. So for left hand, the left side of the function, we say what's happening is x goes to negative infinity. And for right hand behavior, we look at what happens when x approaches infinity. So basically look at what happens when we put in really large numbers. Negative for left hand behavior, really large number positive for right hand behavior. So here we're going to use a graph to describe end behavior. And then we're going to support the conjecture numerically. So the first thing we do is we look at the graph. As we are going to really large negative x values, what is happening, and then what is happening when we go to the really large x values. So if you look at this graph, you'll see that they are approaching this boundary line here, it looks like. So if we're going farther and farther to the left, as we get to negative infinity, it looks like our limit is approaching a 1, because it looks like we have an asymptote at y is 1. Then we look as we go positive infinity, we're also approaching 1. So both ends are approaching 1 the way it looks. So to do this numerically, what you'll want to do is on your calculator, do your table set. So you're going to plug your function in to y equals, do a table set on your calculator for start at negative 100,000, do a step of 10,000, and see what you get for values at really large negative numbers. So if you look at on a table on your calculator, if you look at negative 10,000, it equals 0.999. And if you look at negative 20,000, even farther to the left, it approaches 1. And if you look at all the numbers below negative 20,000, they're all 1. Do the same thing for the high end, for the right side. As you get to 10,000 on your table, you should show me 1.0001. And then when you go to 20,000, you also have 1.0001. And as you keep going, you get to 1 again. That's how you support it numerically. Show me some x values from your table, like negative 100,000, what's it look like it's going to? Do the same thing with your positive numbers. And like I said, I would use a table set starting at a negative 100,000, sets of 10,000. Give me a couple values for the left side and the right side to show me what your limit is. All right, so again, we have another one with end behavior. Use a graph to describe the end behavior and then support it numerically. So the first thing you look at is your graph. This graph does go on forever. Adding arrows and Desmos is not the easiest thing, but these do go on forever. So as we go to negative infinity, as we get farther and farther in the negative numbers, we are going to get to negative infinity. And as we go to the positive side, as x's increase, we are going to positive infinity. Our graph is going higher and higher on the y. Again, use that table, put this in your y equals, your function there at the bottom, into your y equals. And if you see at negative 10,000, you get a number back that looks like this, negative 5e to the 11th. What that means is a scientific notation. You have negative 5 with 11 zeros after it. It's going to a negative infinity. When you check 10,000, you will see it's at 5e to the 11th, which means you're going to 5 with 11 zeros after it. Really large numbers, you're going toward infinity. It's going to get bigger and bigger and bigger. Show me some of these large values you get back from your table. All right, now we're going to use logical reason to determine end behavior of a function as x approaches infinity. So here we have f of x equals 1 over 2x cubed. if you think about this logically, if we put in a very large number for x, let's say I put in 10,000. We're actually throwing at infinity, but what if I put in 10,000? We're going to have 1 over 2 and 10,000 cubed. Well, the number in our denominator is going to get really, really big. And we're going to have 1 divided by a very, very large number. And 1 divided by any really, really large number goes to 0. It's going to get closer and closer and closer and closer to 0. It'll never get to 0, but it'll get really, really close. To be 1 over a very, very, very large number. So as x approaches infinity, we approach 0. Now we look at f of x equals 2x squared over x. One of those things we can do with some of these functions is we can think about what would happen if we put in infinity in here, a really large number again. Let's say we said 10,000 squared, and we divide by 10,000. What is growing faster? When you look at this, the numerator is growing faster. When you're squaring things, really large number, they get faster. They get larger faster than our denominator will. This is going to approach infinity because our numerator is growing at a much faster rate than our denominator is because we're squaring the numerator. So we are going to go bigger and bigger and bigger and bigger, and we're going to approach infinity. Algebraic, you look at this also, you could simplify this, and 2x squared over x is the same as 2x. 2 times infinity, infinity. That's an algebraic way of doing it. We'll do more of that later on this year, but that's another way to look at these. When you look at f of x equals 3x cubed plus 2x, and it's over 6x cubed plus 5x squared, when you look at these logically, and you have, what we basically have to look at is this part right here, our larger pieces, our highest exponents. We have 3x cubed over 6x cubed. We'd have infinity cubed over infinity cubed, right? Well, let's basically cancel out. And all we're left with is a 3 over 6. The higher the power is in the numerator is what's going to drive that numerator's behavior. In the denominator, that same thing, that higher power is going to drive the denominator's behavior. What we end up doing is canceling out the x cubes, and we're left with 3/6. This is 1/2. This will approach 1/2. These other parts on the end don't have as much influence on our functions as we get very, very large x values. What matters is the highest exponents. Those are the ones that are going to drive the behavior of the function. And since we have the same power in both the numerator and denominator, it's just going to be the coefficients dividing out. So 3 over 6. This is how we look at these logically. You know, is the numerator growing faster than the denominator? Then we're going to infinity. Is the denominator growing faster than the numerator? Then we're going to 0. Are they growing about the same pace? Then we're going to take the coefficients off of the powers that are the same between the numerator and denominator. That is all for section 1.3 day 3. Today we use limits to describe the end behavior of functions. Thank you for watching and have a nice day.